There's no number that repeats itself, right?
Yeah, does it repeat or come up again?
Alright, using the popsicle sticks to call on some folks. Melody, can you share with the class one of the words that you and your partners determined were new to help us describe irrational numbers? Not your definition, just the actual word. Can you make sure that Karima can hear you? Because I can hear you, but she can't.
Wait, what was it? He said that he was saying something about an unterminal number.
Okay, I'm hearing the word unterminal. Is that one of the words that you...
Non-terminal.
Non-terminal. Okay. And now you're changing it to non-terminating. Okay, I'll give you a pass on that because it might have been a new word for us, but it's also right here, non-terminating. So if you need to write it down to not confuse yourself. I think these might have similar definitions, but the word that we were looking for was non-terminating. One of them. Jeremy is not here. Also not here. Karime. You and Donovan, when you were coming up with your own definition for non-terminating, what did you two decide was an appropriate definition for non-terminating?
Irrational?
That's a definition for non-terminating. Thinking about the word non and the word terminating. That's what you and Donovan talked about?
I don't know.
Sarah, what did you and or Diego talk about for non-terminating?
It doesn't end.
Doesn't end. Okay, non usually means no, or in this case, doesn't. Terminating, in this case, referring to end. So it doesn't end. Did anyone come up with a different definition? Let's hear from Diana. Did you and your partner come up with a way to phrase non-terminating, doesn't end, keeps on going? Now, asking for a volunteer, did anyone come up with a different way to phrase keep on going, doesn't end, Sergio?
Repeats?
No.
I'm sorry.
I'll include that, but I think you're jumping ahead and thinking about the next word. Donovan. We're jumping on to the other one. I want to include under our definition, some have said goes on forever, right? So if it's not terminating, it doesn't end, keeps on going forever. The other word that I heard you say, Donovan, was non-recurring. And for this, Sergio, it seems like you and your partner did come up with a definition for this in your own words. What did you all think non-recurring meant?
On what?
Non-recurring? What did you just say you thought that was the definition of?
It doesn't repeat or come up again.
Doesn't repeat, or what was that second part you said?
Come up again.
Or come up again. Did I get any other definitions from other groups, Julia?
Has no pattern.
Okay, has no pattern. We'll talk about that shortly. Any other ones that groups think aren't represented up here? Okay, I want to point out and highlight the no pattern, because that can be tricky. When the lady on the video was talking, she said some funny decimals like 1.010010001, right? Now, I do want to talk about this because you're right. There is a pattern, right? She's just adding an extra 0 each time. So the next one in that pattern would be 00001.
How come the zeros aren't a pattern?
Great question. So in that definition, when we're talking about there being no pattern, it's specifically no pattern that repeats, right? So even though there's a pattern here that you guys can see, right, and you can probably continue it, the fact that it's not 0, 1, 0, 1, 0, 1, 0, 1, it's not a pattern that repeats every single time, that's what makes it non-recurrent.
So it's always different, even if it's based on one digit?
Yeah, so it's always different. So even if there's a pattern, it's a non-repeating pattern. So for example, a pattern that repeats is 0.3333, and so on, right?
That's
In
right.
fact, you guys have seen this one before
That's why you say repeating.
as 1/3. This is a repeating pattern, yes. One also thing that I want to include about non-terminating, a lot of students are turning in checkpoints that they're trying to demonstrate are non-terminating, but forget to include these ... the ellipse that you guys are learning in English class. If you do not include that ... I'm going to assume that this actually ends right here. And so if you're trying to show that it's a decimal that goes on forever, you need to include that ... How do you know that it goes on forever? Well, if you are trying to tell me on a checkpoint that it's going on forever, you want to include this, like last exit ticket. I asked you to give me an example. So if you want to tell me that it goes on forever, use the ... As to your question, how do you know? Well, today we're going to find out some more numbers that are going to go on forever. And those are irrational numbers that are non-terminating and non-repeating. Great. Other questions, Eric? All right, let's look at this image that we've seen before. And I think, Melody, this is going to help answer some of your questions. We saw an image similar to this last class where we talked about why the numbers in the middle, the red diagonal, why they were special or important. Can anyone try and recall and share with the class why the red numbers in the middle highlighted were special? Tiffany, what was special about the red numbers? Okay, perfect squares. Yes, that is true. Can you explain what a perfect square is in your own word?
Something multiplied by the same thing.
Something multiplied by the same thing?
The same number.
By the same number. So can you use that to explain how 36 is a perfect square?
6 times 6.
6 times 6 makes it a perfect square. Yes, Jair? There you are. Can you help us explain how we know that 64 is a perfect square?
8 times 8.
8 times 8. Great. Dennis? How do we know that 7 is a perfect square? Sorry, 49.
Just killed it.
Just kidding. Don't answer that one. How do we know that 81 is a perfect square?
9.
What about 9?
9
9
times 9.
times 9. So all these perfect squares are that perfect squares because they are made up by a whole number multiplied by itself. So in this case, 9 times 9. What we're going to do right now is we're going to examine the square root of non-perfect squares, such as the square root of, let's say, 37. If I look at the red diagonal, I could imagine that I would find 37 not in between 16 and 25, not in between 64 and 81, but in between 36 and 49, right? 37 is in between these two perfect squares. So I might want to, on a multiplication chart, point out that it would fall somewhere in between right there, which would tell me that the square root of 37 is going to fall in between these two whole numbers, 6 and 7. Because 6 times 6 is 36, 7 times 7 is 49. So the square root of 37 is going to be some decimal between 6 and 7. So it could be 6.1, 6.2, 6.3. Right now we're not focused on what that decimal actually is. We're just looking for the range. Because sometimes it's going to be helpful to just approximate what is the square root of a non-perfect square. And right now it'll suffice to just say it's between 6 and 7. Because 37 is in between the perfect squares 36 and 49. And that tells us that the square root of 37 will be between 6 and 7. I'm going to leave this up right here. I'm also going to provide you with your own. You're going to be looking at the square roots of 4 non-perfect squares with your table partner. Dennis, do you have an observation? Say that out loud.
What did you do? You erase everything?
Right, but 6 times 6 is 36. The 4 perfect, non-perfect squares that you're going to examine right now are the square root of 7, 23, 50, and 98. I'm going to give you 5 minutes with your table partners and the multiplication chart that I'm about to hand you. Go ahead and come up with the range of the square root of those non-perfect squares.